So now on to how we hear. The technical term for hearing, folks, is audition. And you'd need to know some of the anatomy of the inner ear, the middle ear, to understand how audition happens in a bottom up sort of way, the biological chain reaction that happens. Now, with vision, we know the process started with light in the environment, bouncing off of objects and entering our eyes. With audition, hearing, we need to understand that the process starts with vibrations in the air around us. These are called sound waves. Whenever there's anything happening in the environment that makes um, the air ripple as a consequence, sound waves travel, and those sound waves will enter our outer ear, our ear canal, and set off a chain reaction. I've listed the order here on the left, so let's check this out and make sure it makes sense. As the sound waves, the ripples, the vibration of the air, enter our ear, the first place those vibrations are going to strike or hit is going to be this. This is the tympanic membrane. That's a technical term for it, tympanic membrane, also known as the eardrum. It's this little tissue. That's the first place that's going to be struck by vibrating airwaves, sound waves. Will strike the eardrum, and then the rest of this early process is going to be all about passing that vibration on down the line. There's a chain reaction here that's going to continue to happen. So the eardrum is struck by vibrating sound waves. In turn, this little tiny bone here is going to start vibrating as well. Okay, it's attached to the eardrum. It's called the hammer. Now, the hammer is part of a 3 little tiny bone series that's in the middle ear here. We've got the hammer, the anvil, and the stirrup. 3 tiny bones, and their whole job is to wiggle, to vibrate, in order to pass this vibration along, the vibration that started in the environment. Right now, my vocal cords are vibrating because I'm speaking. I'm causing vibrations in the air that are going into my computer's microphone. You're playing it in, out of your device. Those sound waves, those vibrations are coming out of your device's speakers. The vibrations go all around your room. Some of those vibrations go into your outer ear, and those vibrations are simply passed on. They're picked up by the eardrum, which makes the hammer wiggle and vibrate, which then strikes the anvil. Think hammer, anvil, like a blacksmith has a big hammer and he'll smack iron on an anvil. Did I say hammer? He has a hammer and he smacks the anvil to shape a sword or horseshoe or whatever. So the hammer wiggles, strikes the anvil, which also then wiggles, and then that's attached to the stirrup. This little U-shaped tiny bone here is then made to wiggle, passing the vibration onto the oval window of the cochlea. The stirrup is hooked to the oval window of this bone structure. It's this snail-shaped bone structure called the cochlea. The cochlea, we'll look inside in just a second and see what's going on there. But first, let's realize, with any hearing impairment that happens, let's understand the basics of hearing impairment. There's 2 types of hearing impairment, 2 categories, basically, that we need to understand. There's conduction hearing loss. Conduction hearing loss, that's when there's some problem out here before the cochlea. Okay, maybe a person has rigidity in their hammer, anvil, and or stirrup, where they're just not wiggling like they're supposed to. Maybe they're not passing on the vibrations like they're supposed to. Well, that's going to lead to hearing loss, because all these tiny parts are supposed to pick up vibrations from our environment and pass those vibrations on to the cochlea. If that's not happening, if somebody has a ruptured eardrum, then the hammer will not be as sensitive as it usually is. There will be some conduction hearing loss. But then you've got what's called sensory neural hearing loss. Sensory neural hearing loss is any damage, is caused by, I should say, any damage that's happening in the cochlea, which we'll look at in a second, or after the cochlea. So look here at the auditory nerve. By now we should know that a nerve is a bundle of, fill in the blank. I can't hear you, but hopefully you said axons. A nerve is a bundle of axons. The cochlea is where we're going to find the receptor cells for hearing. And those receptor cells have axons. Those axons bundle up together and leave the cochlea heading toward the temporal lobes, okay, via this auditory nerve. So when we see what happens in the cochlea, let's understand the message is going to be sent down the auditory nerve to the temporal lobes. So more on sensory neural hearing loss in just a minute. Before I get off this slide, I want to detour for a second. Let's move off the topic of hearing for a second, and let's look at these pretzel-shaped tubes in the inner ear, the middle to inner ear. It doesn't say so on this diagram, but folks, we've learned about this otherwise. These tubes are called the semicircular canals. The semicircular canals. These pretzel-shaped tubes are the root of what's called our vestibular sense. Okay? We always talk about having 5 senses: hearing, smelling, seeing, touching, tasting. But we actually have more senses than that, and the vestibular sense is one of them. The vestibular sense is our sensation of our body's orientation. We take this for granted all the time. We almost never have to really pay attention to this, but it is a sense that we have. Like right now, I have a sense, even unconsciously or subconsciously, semi-consciously, that I'm sitting upright. I'm not leaning to one side or the other, even though I've got some crazy effects going on because of the bad lighting in my basement room where I'm doing this recording, and the background's playing with. Anyway, enjoy the graphics there. But my brain understands I'm not leaning, I'm not lying down, I'm not upside down, hanging from my feet from the rafters somewhere. I'm sitting straight up. Don't even have to think about it. My brain knows that that's happening. That's partially because of my vestibular sense telling me, hey, you're sitting upright, you're straight, you're looking forward. Okay? So what's happening to get me to have that sense is inside these semicircular canals, talking about the vestibular sense now, there are sacs of fluid. They're called vestibular sacs. You can't see them on this diagram, but whenever we move our heads, whenever we jostle around, those sacs of fluid inside these tubes, they move around. They jostle around themselves. And in turn, that sends messages to our brain telling us whether we are sitting down, leaning to one side, hanging upside down, or whatever. Okay? This is partially why, if you ever ride a thrill ride at an amusement park, a roller coaster, and you're jostled all around and you're taking, fast turns and going upside down in loops and all that crazy stuff, when you get off that coaster, you might have a little trouble getting your balance at first because your vestibular sacs inside these semicircular canals, those sacs were jostled all around on the roller coaster. So when you step off the roller coaster, maybe it takes a few seconds for those vestibular sacs in your inner ear to settle down and get back to normal. And in those few seconds, you're going to have this confused sense of your own orientation. Okay? That's all a fancy way of saying this. You ready? Here's a quick summary of what I just said. Your vestibular sense affects your awareness of your body's orientation. But in reality, what that means is it affects your balance. Okay? some of you have asked me before, Mr. Otter, I heard when you have an inner ear condition, it can affect your balance. You'll get dizzy really often. Yeah, because your vestibular sense is rooted in your inner ear. If you have an ear infection and this canal here is all clogged up with fluid or whatever, it can put pressure on these semicircular canals and keep them from operating properly. So if you got a really stuffy head, sinus issues or whatever, it can make you feel really lightheaded and woozy and dizzy because that pressure is affecting your vestibular sense. It's rooted in your inner ear. Okay? So the vestibular sense, in reality, it affects your sense of balance. It helps you not be dizzy, helps you understand your body's orientation in space. Now, you might be thinking, Mr. Ryder, we learned before that the cerebellum affects balance. Yeah, it does. The cerebellum's in the brain, okay? A very primitive and old part of the human brain that absolutely affects our sense of balance, our ability to balance, our coordination of movements. Just understand the cerebellum isn't the only part of our body that affects our balance. The vestibular sacs inside these semicircular canals also affect our sense of balance. Working in conjunction with the cerebellum, they're kind of a team, okay? So I wanted to make sure you understood that because we have a real clear picture of it here on this diagram before we move on with hearing. These vestibular sacs, these semicircular canals, they don't affect hearing at all, but they affect our vestibular sense. And I wanted to make that clear before moving on. Okay, let's get back to hearing. So here's the other ear. Now we're looking at the same process in a black and white picture coming from the opposite direction. Sound waves come in through the ear canal. They strike the eardrum, which strikes the hammer, which strikes the anvil, which strikes the stirrup, which is hooked to the oval window of the snail-shaped cochlea. Now, inside the cochlea, we've got those receptor cells we were talking about. Here you can see the semicircular canals again, and look at this auditory nerve leaving the cochlea heading toward the temporal lobes. But it's inside the cochlea, we have a zoomed in shot here, that we see these cells. You kind of have a picture of a cell body here, and these are the axons of the receptor cells moving away to form the auditory nerve. And these out here, kind of, they're hair cells. The receptor cells inside the cochlea are little cilia, they're hair cells. And they're in this part of the cochlea called the organ of Corti on top of this little thin tissue called the basilar membrane. Without getting too fancy, just understand if they ask you on an FRQ or something like that, what the basilar membrane has to do with something, it affects how we hear. That's really all you have to know. The basilar membrane is this thin tissue inside the cochlea that's going to ripple, okay? The basilar membrane is going to ripple when the fluid inside the cochlea ripples. Remember, we've learned that sound is starting out having everything to do with vibrations in the air, passed on through these three tiny bones in the middle ear, the stirrup being one of them. That stirrup vibrates and wiggles the oval window of the cochlea, and that makes the fluid inside the cochlea vibrate as well. And that in turn makes the basilar membrane vibrate. And that in turn makes these little hair cells bend. Okay, if you imagine my fingers being the hair cells inside the cochlea, okay, attached to the basilar membrane, when those hair cells bend in response to all this vibration inside the cochlea, that's what makes those hair cells, look, send messages down their axons, down the auditory nerve to the temporal lobes. All about vibrations, okay? The vibrations inside the cochlea, including on the basilar membrane, make those little hair cells bend, and that's what stimulates those cells when they bend in response to the vibration to fire their message to the temporal lobe. Okay? That's what we just said. Now, remember how we brought up sensory neural hearing loss? Now this can make a lot of sense. If there's any damage inside the cochlea, a person's going to have hearing loss in some way, shape, or form. One of the most common types of hearing impairment is called tinnitus. Tinnitus is when a person has a very high pitch ringing in their ears, they hear it all the time, high pitch ringing, and it basically interferes with a person's ability to hear anything else. Well, sometimes that ringing in our ears can be very temporary. When you suffer from tinnitus, it's a permanent ringing in the ears. And here's what happens. Tinnitus is caused by exposure to loud sounds. It could be a one-time exposure, it could be over time. What happens is with intensely loud sounds, those hair cells in the cochlea are going to bend tremendously. They're going to bend a lot. Okay? So much so that those hair cells can become damaged. And if they're damaged, they never straighten up again. They never go back to normal. So what we've learned is whenever those hair cells bend a bunch, they're firing signals to the temporal lobes, telling our brain that we're hearing stuff. So imagine you're at a loud concert and you're standing right by the PA or whatever, the music's blaring, it's so loud that it bends those hair cells tremendously, and you're in that concert for a few hours. So those hair cells stay bent even when you leave the concert and you walk to your car. Maybe you got separated from your friends and you know they're going to meet you back at the car. You get to the car, open it up, get inside and shut the door. Well, these hair cells in your cochlea are still bent. Even though you're sitting in now a silent car, there's nothing to hear. It's silent inside your car, but these hair cells are bent. So that means they're still sending messages to your brain. Pizonk, 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 because they think they're still being stimulated by sounds. They're sending messages to the brain, but you're sitting in a silent car. How about for the millionth time, I ask this question. What is your brain always doing for you? Making sense of stuff, right? Making sense of stuff. So if these hair cells are bent and they're sending their messages to the brain saying, we're hearing stuff, but there's nothing there to hear because you're sitting in silence, the brain has to make sense of, well, I guess I'm hearing something. I'm getting messages from these hair cells. I guess I'm hearing something. What could I be hearing? And the brain interprets that silence as that high pitch, annoying squeal. If you're lucky, those hair cells in a day or a couple days, maybe those hair cells will straighten up again and the ringing will go away. But it is possible to permanently damage those hair cells. They will stay bent potentially for a person's whole life, and that's what causes tinnitus. And that's why you should be very careful. Dad mode right now, just to be warned, right? You should be careful about how loud you turn up your headphones, your earbuds, how loudly you listen to music, the abuse you put your ears through. I've been guilty myself in the past. It's terrible stuff to think that you might, at a young age especially, permanently damage those hair cells in the cochlea and cause tinnitus, just one form of sensory neural hearing loss. Okay? Other types of sensory neural hearing loss, well, if there's a problem in the auditory nerve, look, everything might be fine in the cochlea, before the cochlea, in the middle ear with these tiny bones, maybe everything's fine. But if these hair cells send their message and then there's a problem in the auditory nerve, that's going to cause hearing loss. Or maybe there's no problem there, but maybe there's like a cortical hearing loss, meaning there's some problem in the cortex of the brain, in the temporal lobes. If there's some kind of damage from a stroke or a car accident, neurons have been damaged in temporal lobes, that could cause hearing loss as well. Okay, so to recap, conduction hearing loss is caused by damage that happens, location-wise before the cochlea. Hammer, anvil, stirrup, or the eardrum. And sensory neural hearing loss is caused by any damage that happens in the cochlea or afterwards, auditory nerve, temporal lobes, what have you. Okay, as you're hearing this, you've got messages coming out of your device in all the ways we just explained, sending messages to your brain's temporal lobes right now. Now, before switching to the next slide, I want to discuss one final thing about the basics of hearing, and that is about sound localization. Sound localization is a fancy way of saying you're able to determine where sounds are coming from. With your eyes closed even, you can tell, generally speaking, where sounds are coming from. If somebody calls your name from this direction, you'll know typically right away that, oh, what? That they're calling you from that direction. That's because with all these processes we've just discussed with hearing, there's one more factor to add. That is that most of us have an ear on each side of our head, right? And when somebody calls our name from over here, or if we're listening to music and there's stereo sound, I know the Beatles were really big in this, like dividing different instruments into each speaker. If you listen to a Beatles recording, you'll hear, some guitar in this, left speaker, and the bass guitars in the right speaker, and certain drums are in one speaker, and other instruments, organs, keyboards are in the other speaker, and they'll even pan back and forth and have this really weird, kind of surround sound effect on you. We watch a movie in surround sound and it sounds like a car is, coming from your left and speeding by in front of you and moving to your right. The question becomes, how do they do that? How do they give us that illusion of sound movement? It's because the people who produced the movie or those, songs, they understood how we locate sounds. And it comes back to this. Most people have an ear on each side of their head. And sound waves come from anything in the environment, which might cause them, to ripple vibrations in the air. Here it is, folks. When those sound waves enter one ear first, and then another ear sometime later, even a fraction of a second later, that time difference between the sound waves entering one ear and then the other, that time difference is what tells the brain, oh, the sound's coming from over there. The snap happens over here. Those sound waves are going to enter my left ear first before those sound waves surround my head and go into my right ear. That little bit of time difference is all the brain needs to be able to interpret, oh, that snap came from that direction. Okay? That time difference is necessary for the brain to interpret where sound is coming from. Okay? With that, let's get to some other basic theories on hearing. I don't want to dig too deeply in this, but let's go over some of the basics. With volume, how can we tell when something's quieter or louder? Generally speaking, it has to do with how much those hair cells are bending. If I whisper or talk quietly, the hair cells in your cochlea might bend just a little bit because there's only a little bit of vibration happening, inside the cochlea to make the hair cells bend like that. If I speak louder, the hair cells are going to bend more because they're responding to even more rippling inside the cochlea. That's pretty simple, right? How about pitch? That's where things get super complicated. How can we perceive if, someone has a very high pitch voice or a very low pitch voice? Like, what vibrations are still happening the way that we've learned it. So how does it occur? Well, quickly, there's two theories that try to explain how we differentiate pitch. One is called place theory. And what place theory basically states is that different parts of the basilar membrane will ripple based on whether it's a high-pitched sound or a low-pitched sound. So remember, the basilar membrane is just a thin tissue It surrounds the inside of the cochlea, that snail-shaped bone in the inner ear. The basilar membrane is where we find those hair cells, remember? So the theory is that there's just different places on the basilar membrane that will wiggle. So maybe when we hear a really high pitch, there's a certain part of the basilar membrane that will ripple in response to that high pitched sound. But if it's a really low pitched sound, maybe there's a slightly different area of the basilar membrane that ripples. And somehow the brain knows if receptor cells are firing from this place of this part of the basilar membrane, the brain just knows we must be hearing a very low pitch because those particular receptor cells are bending in response to the vibrations. That's place theory. The other theory is frequency theory. I think this one might be a little more popular. Frequency theory basically states that we distinguish pitches because receptor cells will fire more frequently depending on what the pitch is. Like maybe if it's a very high pitch, I can't get super high, but if it's a super high pitch, I'm doing my best. Maybe those hair cells are firing very frequently, telling the brain it's a high pitched noise we're listening to. And maybe they don't fire as frequently if it's a very low pitch we're hearing. Okay? Fewer firings in order. But there is one limitation to frequency theory, not one we can't work around. But remember, when we learned about neurons, and receptor cells are a lot like neurons, we learned that there's this thing called the absolute refractory period. That's the little bit of time, it's a time period, after a neuron fires. The same holds true for a receptor cell. When a receptor cell fires, bzonk, a message to the brain, it has a little fraction of a second where it cannot fire again, at least not right away. It takes another fraction of a second for that cell to reset itself, to maybe repolarize, to be ready to fire again. Well, that posed a problem with this theory, this frequency theory, because if you're saying, oh, we can hear high pitches, as long as these receptor cells are firing again and again and again and again, telling the brain it's a high pitch. But hold on, those receptor cells need a tiny bit of time to reset before they fire again. So it seemed like frequency theory might have been incorrect until somebody came up with this idea, this addition called the Volley principle. The Volley principle says, look, frequency theory is right, but these hair cells must work in teams. Like let's say teams of 3. We'll isolate 3 little receptor cells here in the basilar membrane, inside the cochlea, and maybe frequency theory is true, but it has to happen like this. Instead of these receptor cells firing like this, all at once, maybe they happen like this. Bizonk, fire, and then bizonk, fire, and then bizonk, 1, 2, 3. If that happens, if they volley like that, 1, 2, 3, then by the time the third cell fires its signal, the first cell in the trio has had time to reset itself, to fire again. That's the Volley principle that makes the frequency theory maybe legitimate. Again, instead of bizonk, all 3 hair cells bending and firing at once, maybe they fire in quick succession. Bizonk 1, bizonk 2, bizonk 3, then this one's reset at the beginning. Bizonk 1, and by then, these other 2 cells have had time to reset again. Bizonk 2, bizonk 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. That's how you could have receptor cells firing very frequently so that we could perceive certain pitches. Alrighty, folks, that's hearing. We will continue with some issues of perception in the next chunk. See you later.